Today we will discuss how to calculate transition probability for constant potential. Okay, that means constant potential means here we come in time dependent perturbation theory. We know the Hamiltonian is split into two parts. V of t, where V of t is the perturbing potential. That's what we are giving externally to the system. Okay. Last class we have discussed the transition probability for different potentials, and we have taken some, I think, exponential potential. That in last class we have taken exponential potential, time dependence on this potential. Okay. Today we will discuss this transition probability for the constant potential. That is potential here. Potential is switched on when time t is equal to 0. Okay, t is equal to 0. The potential is switched on. Okay, so t is equal to 0 only potential is started. Then up to some time t, up to t, then the potential is constant. Okay, that is potential is constant during this time. V of t is constant. At t is equal to 0 to t, V of t is constant. Okay, that type of potential we are applying. Okay, that is it is constant throughout the interval 0 to t. So what happens? So how we will calculate this transition probability for such a potential? Okay, here we have to calculate the transition probability from a state, say in last class also some state I to f, right? The final state is ket f, initial state is ket I. So in last class we have found the equation for transition probability, that is transition probability from the state I to f is given by, remember it is 1 by h cross square modulus square of what, integral 0 to t v fi, remember t dash e raised to I omega fi t dash dt dash, right? Dt dash, this modulus square. Okay, today today we have to calculate this transition probability for this problem. So V of t is constant. Okay, that is in this interval there is no time dependence, it is constant. Okay, so this can be calculated. First you have to calculate the integral of this. What is the integral of this equation? Then we will take modulus square for calculating this transition probability. So we will calculate. Okay. First we will calculate 1 by h cross integral 0 to t vfi. Okay, vfi, then t dash. No, it is constant, so you just write vfi. Then e raised to I omega fi t dash dt dash. So I am just taking vfi outside. You remember what is this vfi? H cross integral 0 to t e raised I omega fi t dash and dt dash. Omega fi, you remember, is this ef minus ei by h cross, right? Ef is the energy of the final state, energy eigenvalue of the final state, the energy eigenvalue of the initial state. That is the energy difference or energy gap between the initial and the final value. Okay. So if you do this, what you will get? It is vfi by h cross integral 0 to t, right? This integration is very easy, so I hope you people know this. Right? It is e raised to I omega fi t dash by I omega fi, right? Then give 0 to t. Okay. Then So I am going to give the limit for this, which is e raised to I omega phi t minus e raised to 0 1. So I will get v phi by h cross e raised to I omega fi t minus e raised to 0 1. Okay, 1 divided by I omega fi. Okay. Now we have to calculate omega w or transition probability. So you have to take modulus square, that is Vfi by h cross square then e raised to I omega fi t minus 1 by I omega fi square modulus square. Okay. Now you have to take care of this. Okay. Now you take care of this by taking, you have to square it, that you remember e raised to I omega, you have to take complex conjugate of this quantity. So you do it, you will find out what it is square. Okay, it's equal to Vfi by h cross square, and omega fi we have to take inside, then this square, so this actually square Vfi. Then what about this? I into minus I, that is okay. I into minus I is I into I minus 1 minus plus 1, so it won't affect. Then this quantity will be, if you take the complex conjugate, e raised to I omega fi t minus 1 multiplied with e raised to minus I omega fi t minus 1. Okay. Then plus I and minus I is there, that will be 1. So we have to, we don't care. So this, if you multiply this, then you will get actually e raised to I theta minus 1 e raised to minus I theta minus 1. That will be, you do it, that will be what? If you do that, if you do this, e raised to I theta, right? E raised to I theta minus 1 into e raised to minus I theta minus 1. Okay, you can do it. E raised to I theta is cos theta plus I sin theta minus 1, or you can directly do like this. E raised to I theta and e raised to minus I theta, it will be 1. Okay, e raised to I theta, e raised to I theta multiplied with minus 1. Okay, minus 1 into e raised to minus I theta. Okay, minus 1 into minus 1 plus 1. Okay, 1 plus 1 2 minus e raised to I theta is cos theta plus I sin theta minus c cos theta plus I sin theta minus cos theta plus, sorry, e raised to I theta, this is correct, right? E raised to I theta and e raised to minus 6, so 1 e raised to minus e raised to I theta, then minus 1 into e raised to minus I theta, then plus 1. Okay, 2 minus e raised to I theta plus e raised to minus I theta. Okay, minus is common for this. Okay, now e raised to I theta plus e raised to minus I theta is equal to cos theta plus I sin theta plus cos theta minus I sin theta. Okay. Now cancel 2 cos theta will be there. Okay. 2 minus 2 cos theta, that is 2 into 1 minus cos theta. Okay. So I am going to substitute here e raised to I omega is Vf I square. This will be 2 into 1 minus 1 minus cos omega Fi t. So this will be, this transition probability will be, okay. So problems are just നോക്കാനേ ഉള്ളൂ, പക്ഷെ ഇത് എന്താണ് കുറച്ച് ഇമ്പോർട്ടൻ്റ് ആണ്, എപ്പോഴും ചോദിക്കാം. H cross square 2 is there, okay, right? 2 is there into 2 1 minus cos square, right? This 1 minus cos theta is equal to 2 sin square theta by 2. Okay. Finally, you will get, okay, 2 into 1 minus cos omega theta is equal to 2 sin square theta. 2 into 2, it is 4. Okay, 4 Bfi of modulus square H cross square omega Fi square, this is sin square omega Fi t by 2. Okay, the final expression will be like this. This is